When a Category 4 hurricane hits a major metropolitan area, the physical damage to infrastructure guarantees widespread, catastrophic power grid failures. To minimize this chaos, a local utility company spends months building a machine learning model to predict exactly which neighborhoods will lose power when the storm makes landfall. This chart shows lab results. Predicted outages align perfectly with historical data. By technical standards like mean squared error, performance is flawless. But checking the timeline axis reveals a problem. The prediction is generated exactly 60 minutes before impact. Utility managers face a rigid physical constraint. Mobilizing heavy equipment and deploying human repair crews across a massive grid takes a minimum of 48 hours. A flawless 60-minute warning leaves the trucks parked. The model achieved absolute technical perfection in the lab, yet the business still failed to restore power any faster. In machine learning, technical success and business success are entirely different things. Building a machine learning product requires navigating the cross-industry standard process for data mining, or CRISP-DM. It is a cyclical, non-linear framework, meaning teams constantly loop back to previous stages when new constraints are discovered. The utility company didn't make a mistake in their data gathering or modeling phases. Their project failed at step 1, business understanding. Data scientists measure technical performance using an output metric. These are the scores, like accuracy, precision, or recall, that track how well an algorithm identifies patterns. But product managers most prioritize the outcome metric. This is the tangible, real-world result that matters to the organization, like reducing the total hours a city spends in the dark, or cutting operational costs. You must define the required business outcome first. Only then can you determine what technical output score is actually required to support it. Blindly optimizing for a 100% technical output score often creates a product that breaks under real-world constraints. Dense neural networks might offer marginal gains in accuracy, but they sacrifice interpretability. If human operators need to understand why a prediction was made before taking a risky action, a complex black box model is useless to them. Then there is the sheer financial cost. The server fees and computational power required to ingest, store, and process massive data sets for a highly complex model can quickly exceed the money that model was designed to save. To avoid engineering and expensive failure, teams have to iterate. They build simple heuristics and test basic mockups with users, only investing in complex machine learning when early feedback demands it. Managing computational budgets, ensuring explainability, and enforcing strict time constraints are core product requirements, rather than secondary engineering afterthoughts. You will never know if you achieved your target business outcome while your model is still sitting in a controlled lab environment. Achieving a high score on a test dataset only proves that your algorithm didn't memorize the training data. It confirms you avoided data leakage. It does not prove you solved the user's problem. To measure real value, you have to release the system into the wild. You run A/B tests against standard operations, or conduct beta tests to see how real customers actually interact with the predictions. And deployment is never the final step. As soon as a model hits production, environmental conditions begin to shift, and its predictive accuracy will start to degrade. This diagram shows the required solution, the AI flywheel. When users interact with the product, they generate fresh behavioral data. That new data feeds back into the system to improve the AI, which in turn creates a better product experience. This continuous feedback loop forces the team to actively monitor and retrain their machine learning systems so they can adapt to the unpredictable nature of the real world. A robust machine learning system with an 80% accurate model that actually cuts $10 million in costs will always beat a 99% accurate algorithm that saves nothing.